Chapter 3, Vectors. So in the previous chapter, we studied one-dimensional kinematics, and that is motion along one direction, along one straight line. You can either go forward or backward, and you can either accelerate forward or backward. So you know there are only two possible choices when it comes to directions, and we can simply label one positive, the other one negative. We never have to use the notion of vectors. But as soon as one leaves one dimension, one straight line, and you move on to two directions, two dimensions, then clearly there are infinite number of possible directions. So we can no longer get away with either a positive or negative sign to label directions. We must introduce a quantity with not only the magnitude, but also the direction. And as you know, that is called a vector. So what do we call a quantity with only magnitude but no direction? Now, as you know, that's called a scalar, right? And most of us know clearly what a vector is, what a scalar is. So let me write it down just to be clear. A vector is a quantity with both magnitude and direction, whereas a scalar has only magnitude. So vector, let me write it down. Magnitude plus direction. You have to specify both the magnitude and direction to uniquely specify a vector. Whereas with a scalar, it's magnitude only. And let's look at some examples. This, as you know, is a speedometer in your car. The speedometer reads a number, and that number is how fast the car moves. You notice that we never call it a velocidometer, do we? We only call it a speedometer. So why don't we call it a velocidometer? Because it doesn't give you velocity, it only gives you speed. What is the difference between velocity and speed? Well, speed simply tells you how fast the car moves. It doesn't give you the sense of direction. Whereas with velocity, you have to tell me not only how fast the car moves, but also in which direction it moves, say east or west or whatever. So a vector, so velocity is a vector quantity, and speed is just how much is the magnitude of that vector quantity. So it's just how fast you move, not direction of motion. And since the speedometer doesn't tell you the direction of motion, we can only call it a speedometer, not a velocidometer. So velocity is a vector, and speed is only its magnitude. Okay, so we have here a temperature scale. Is temperature a vector or a scalar? Well, we know it's a scalar, even though we say, oh, temperature goes up and temperature goes down, or rise and fall. When we say it goes up, it only means the magnitude, the reading is increasing. It doesn't mean it's actually literally has a direction going upwards. Okay, so temperature is a scalar. What about this mass, a 10 kilogram mass? Is mass a scalar or vector? Well, mass is the amount of material an object holds. Okay, it has to do with how many atoms you have and how many molecules you have, that sort of thing. So it's basically just a number. It has no sense of direction. Okay, whereas there's a related quantity called weight. You see here, you see a weight scale. The weight scale gives you a reading, right? That is a magnitude. But is weight a scalar with only magnitude? Well, not really. Weight really is the force of attraction by the Earth on us. So it has a direction. It's downwards, right? The Earth attracts towards it. It doesn't push us away. So when we talk about weight, we have an implied direction, and that is it's downwards. Even though we usually don't talk about it, it's understood by everybody what is the direction of the weight. Of course, if you change that direction, it's going to make a huge difference, right? So weight, unlike mass, is actually a vector, even though a lot of people sometimes, interchange and confuse between these two quantities. They're related, but they're not the same thing. Okay, now here is a pair of power cords, and when you plug into power supply, you see a current flowing. So the current can flow like this, but it can also flow backwards, right? It can also flow backwards. It does have two senses. One direction we can go positive, the other direction we go negative. Does that mean current is a vector? Well, not quite, because current is a vector. Then as I reposition the wire, let's say the wire is no longer, pointing position this way. Rather, I'm going to twist the wire so that it now points that way. Doesn't that really change anything? I mean, that would be crazy, right? I mean, if you plug in a power supply, do you have to, orient the shape of the power cord in a certain direction? No, you don't have to do that. It changes nothing, right? So, even though it's got two senses of flow, current is not a vector. It's a scalar. It flows from one side to the other, or from the other side to the first. Either way, there are only two possible choices. Again, we can call one positive, one negative. It doesn't have a true sense of direction, because by twisting the orientation of the wire, you don't change the current at all. Okay, so these are some common examples. But in general, when we have a vector, how does one represent a vector by drawing? It's called graphical representation. Well, it's got a direction, so I'm going to use an arrow to indicate the direction of a vector. Right? And so now I'm going to draw an arrow now. So here's a vector, and this arrow indicates the direction of the vector. And I can also indicate the magnitude of the vector by the length of the arrow that I draw. I can, for example, go from this point to that point, and let's say it represents, this vector is a displacement vector, which represents the position change from initial position. That's where you start. Let's say you start in the morning from your house. This is your, in the morning, it's a starting point, initial. Let me try to make this pen work. Initial. That's the beginning of the vector, initial here. And here's the final point of the vector, final. Let's say the actual distance between initial and final in the real world is 3 miles, okay? But I don't have, size for 3 miles, a piece of paper that big. So I'm gonna, let's say, use 3 inches to represent that. So then every time I draw 3 inches, I know the actual distance it represents is 3 miles. That will be the magnitude of this displacement vector. So again, I can use a arrow to indicate the direction, and the length of this arrow to indicate the magnitude of the vector. Now, a vector is uniquely defined once I know its magnitude and its direction. Right? The next thing I want to talk about is how we do vector algebra, and that is how we do addition and subtraction of vectors. I'm going to start with an example of displacement vectors. Okay, a real world example. Let's say after the class, you're going back from PCC to your house. This is PCC. I have a real map. Okay, part of a real map. So this is Pasadena City College, as you can see here. Let's say your car is parked somewhere here. That's a parking structure somewhere here. This is where your car is parked. And let's say your house is there at the corner of East California and what is this street? San Marino Avenue, somewhere here. Okay, so this is your house. I don't know if you really live there. It's an expensive neighborhood, but you get an idea. Okay, it's just just your final destination. Let's say this is your house. So how do you get there? Well, if there were a direct route connecting the beginning point to the end point, a direct route, you would have driven this way because that would be the shortest and easiest way to get there, right? So you would drive directly from PCC to your house. You would drive something like this. It will be the shortest path. This would be your displacement vector if there was a direct route. Of course, we know that is not the case. There exists no road like this. So you're going to have to make a few displacements. So you're going to start, for example, by driving down on Sierra Bonita. So here's your first. I'm going to use a different color for every leg of the trip. So let's say you're going to start by driving downwards. Okay, so you go you go this way. I'm having a little bit trouble drawing it. Hold on. Oh, there we go. So you drive down to Del Mar, that's the first displacement. And then you're going to make a left turn on Del Mar. And you're going to drive to the east along Del Mar Boulevard. You're going to drive this way. Okay. And then thirdly, once you reach Allen, you're going to make another right turn. Okay, I'm going to use a different color for that. Make another right turn. So this time you're driving down south on Allen. You're going this way. And when you reach California, you make a left. This is the last leg of the trip. And you're going to end up reaching your destination, which is your house there. So you have 4 successive displacements. 1, 2, 3, and 4. And when you add all these displacements up, what is the net result? Then net result is that you went from PCC, which is here, to your house, which is there. So clearly, the sum of all these vectors, and that is the net effect of all these vectors, is equal to this red vector. Okay, so this gives us a way of graphically representing the summation of vectors. Here, in this case, the sum of these 4 vectors. How did I add them graphically? I positioned the beginning of the second vector here at the end of the first vector. Then I put the beginning of the third vector at the end of the second vector, and you keep on going until I reach the end of the last vector. And what is the sum of all these vectors graphically? It is a vector starting from the beginning of the first vector, which is here, which is PCC. The beginning of the first vector here to the end of the last vector there. That's how you add vectors graphically, okay? It doesn't matter how many vectors you have, you can always do that. You can keep on drawing. And if you only have 2 vectors to add, vectors A and B, then you can see how we add vectors by graphics. There are 2 possible ways to do that. Okay, here is, on the right side of this graph, I have A plus B represented by vector A and then vector B. I start with vector A, this vector here. You start from the first vector, which is vector A, okay? And here is the end point of vector A, and you can draw the second vector, vector B. And then you start, and then from the beginning of the first vector to the end of the last vector is A plus B, as I did before, okay? And by the way, oftentimes, especially when we do hand drawing, we add a little arrow on top of A to indicate this is a vector, and then B, we do something like this. In print matters, sometimes you don't see this arrow, but there's a convention when if a quantity is a vector and they don't put an arrow, then what they typically do instead of that is use boldface. So you see all these A's and B's are in boldface, okay? But when we do handwriting, just to make it clear, we put an arrow on top of that. So here's vector A plus vector B by using the same technique that I used earlier here, and that is to put the second vector at where the first vector starts. Where the first vector ends here. And then for vectors A and B, plus with the sum of A plus B, you form what's called a vector triangle. Okay, that's called a vector triangle. And this method of adding 2 vectors by drawing a vector triangle is known as the triangular method. So this side This is the triangular method. Now, look at the one on the left side, this one. Here, you also try to add A and B, and clearly you're getting the same A plus B. You see, this guy and that guy, they're really the same thing, right? Same direction, same magnitude. The difference is in how I do that. You see, instead of starting A and B at different locations, here I started B where A ends, right? It's called tip to toe. For this method, I'm starting both A and B at the same location. See that? Vector B and vector both start from here. And then, in order to get A plus B, I don't draw a triangle anymore. I need to draw what's called a parallelogram, okay? This, as you know, is called a parallelogram. So once I get A and B, I'm going to continue drawing two parallel lines, this guy and this guy, to form a parallelogram with the first original vectors A and B. So you have a parallelogram formed by these four sides, and A plus B really is just the diagonal, okay? It's the diagonal of this parallelogram. So this is called the parallelogram method, okay? The parallelogram method of adding two vectors. Instead of triangular method. They both use the same thing. So you wonder, gee, it would be easier to draw a triangle instead of a parallelogram. Yeah, it's easy to draw, but the parallelogram method has its own advantage, and that is both vectors A and B start from the same location here, just like the sum of A plus B. And why is this an advantage? We'll see that when we represent vectors by numbers. It's called analytical method. What we're doing here is adding vectors graphically. Okay, now I want to make sure that we're on the same page here, and that is, I want to talk about what's called vector transposition. As I noted a minute ago, this vector and this vector are really the same thing, even though they don't start the same location. One is on the left side, the other on the right side of the page. I consider them the same vector because they have the same magnitude and same direction. Okay, so transposition of a vector means I draw a vector here, keeping a certain magnitude, a certain direction. Then I'm going to redraw the same vector somewhere over there. Again, keeping the same magnitude and keeping the same direction. Then I have done what's called a transposition. This vector A, if I call this vector A, what do I call that vector? I should also call it A. It's the exact same vector, okay? There is no meaning to specify where it starts. You can start from here, you can start from here. It doesn't matter where you start. As long as a vector has the same magnitude and same direction, you move it to a new location to start, it's the same vector. This is the reason why this vector I call B, this one I also call B, it's the same thing, okay? And this one I call A, this one I also call A, they're the same thing because it's just a matter of transposition. Now, this means that the origin, the starting point of the vector does not matter. I can make it anywhere I want. So I can move all the origin to the same spot if I choose to. That will be a huge advantage when I turn vectors into numbers. You will see that. Okay, so that's how I add vectors by graphics. You know, the nice thing about the graphical method is that they're visually very clear. I mean, you can see this diagram, right? I mean, it is on this map, right? You can easily see, you know, how we get to PCC back to the house by successive displacements. The problem with that is it's not very practical. If you want to yield high accuracy, you want to ask yourself, how should I drive from PC to my house? Can I represent this on a map, on a scale? Well, yeah, you can draw this, you know, green, you can draw this blue vector first, and then this green vector and this purple vector and so on. But if you draw them precisely to scale, okay? For example, you say, oh, I'm gonna go down Sierra Bonita for say 340 yards, and then I'm gonna go left eastwards on Del Mar for exactly 421 meters and so on. Because if you don't do that, if you don't follow the exact direction and exact magnitude, you're gonna be off. You're not gonna arrive at your house. You see what I mean? So you need to be precise in drawing both the magnitude and the direction of each vector. Otherwise, you could end up in a totally wrong neighborhood. Okay, so this is the pitfall of adding vectors by graphics. Unless you don't care about the accuracy, unless you just want to get a crude estimation, you cannot arrive at a good result by drawing, unless you can accurately draw each vector in the sum. So that's something that we have to keep in mind. And by the way, you can also do vector subtraction. It's not that different from vector addition. Suppose I have vector A minus vector B. What exactly does that even mean? Vector A minus vector B is the same as vector A plus negative vector B. So what is negative vector B? It's the same vector as B, except it's totally reversed. So so if let me draw B here. So here is vector B, and vector negative B would be totally just backwards. Same magnitude, just totally opposite direction. So let me draw vector A plus B now. So here is vector A, and here is vector B, right? Let's say A and B look like this. So A plus B would be like this. All right, A plus B would be this red vector, this A plus B. So what is A minus B then? Well, simple. You have to add A and negative B. So I'm going to draw a negative B now. So negative B, okay, that's a vector going backwards. That's negative B. That's negative B, right? And we have to add A and negative B. That's all I have to do. Just add those two up. So therefore, I end up with a different vector, this one. That is A minus B, because it's A plus negative B. Okay, now in a parallelogram method, if I draw a vector A, if I start with a vector A, and this time vector B starts from the same location, so here's vector B, you know, then I form this parallelogram, right? As you know, this diagonal is A plus B. This diagonal is A plus B. But what about A minus B? A minus B is in fact the other diagonal. This is A minus B. This is A minus B. Can you see that? Well, A minus B is A plus negative B. So let me draw a negative B here. Let me first draw a negative B. You can see why that's the case. Here is negative B, right? Opposite to B. So here's negative B. And then you add A and negative B up by drawing another parallelogram. Aren't you getting this as A plus negative B? But this guy and this guy, they're really the same, just transposition vector. And therefore, you know, you can think of A plus B and A minus B as two vectors. One of them is a diagonal of the parallelogram. The other one is the other diagonal. It's just that simple. Okay, so that's how we do vector addition and subtraction using graphics. It's visually clear, but the accuracy is not guaranteed unless you do precise drawing for each vector. So what do we do next is we're going to look at a more practical way of doing vector algebra to add vectors or subtract vectors. Instead of doing precise drawing, which is difficult, we're going to turn vectors into numbers. So instead of drawing, we can simply calculate. We can work out these numbers to see what is, for example, the vector A plus B or A minus B. So that is in the next lecture.